Alright, we're going to talk about confidence intervals using single sample estimation. So basically now we are moving in a slightly different direction in the course. First we talked about samples and data analysis. Then we talked about probability, distributions, continuous and discrete. And then we talk about the sampling distribution, working with X bars and their properties and the central limit theorem. So now we're going to go back to samples. We're going to collect data, find X bar, but we're going to use those to estimate parameters of populations and also look at how good those estimates are based on these probability rules and properties of the normal distribution that we have studied. So we're going to put all these things together at this point. And so it's going to be fun last two topics. So we're going to start with topics we're going to cover in this chapter: introduction, point estimators and their properties, single large quantitative populations, single small quantitative population, and we'll talk about the binomial population. So when you have, remember about the parameters we have studied. What did we study so far? We studied two kinds of populations: binomial quantitative populations and binomial populations. And in quantitative populations, when we did quantitative, like populations with distributions being the bell shape or the exponential or the uniform, the mean, the parameters we used, needed were the mean. Okay, the mean, we talked about the standard deviation, and we talked about the sample variance. So but among all of these, the mean is the most important. And we said from a sample, the way we compute the sample values were X bar, S, and S squared. So we want to review to make sure that that's what we do. And we call, now in this chapter, we're going to call X bar as the point estimate or estimator. So it's the point, it's the one value that estimates the mean, point estimate for the mean. For the binomial population, we talk about P as the parameter and N is the number of successes, but primarily P as our unknown parameter. And from the sample we looked at the proportion of successes, where X is the number of successes and N is the sample size or the number of trials. And of course we used P hat to estimate P. So that's the proportion of successes in the sample, that's in the population. Remember, in the population, these quantities in the population are unknowns. So we don't know what this is. But we know these. These are knowns here. So we use, because we can collect them from a sample, but we can get those to estimate those values. The question, of course, is how good are these values as estimate of these parameters. One thing for sure is collecting data is very expensive and costs a lot of money. So if your data collection requires you like car crash tests, if you think of these, if each time you crash a car you get one measurement about how good that is. So you need to crash 30 cars to get large samples so you can use the central limit theorem. That's going to be a very expensive sample. So that's why we want to know, we want to work with, if we can deal with it, have small samples, get all the data, and get all the information in that data and utilize it to the maximum possible effect. Okay, so we go to, so we have point estimators and we have interval estimators. We're going to focus on interval estimators because you estimate the parameter with an interval. First, we're going to look at point estimators though. Good estimators have these properties: unbiased, which means the mean of the sample distribution is equal to the parameter. The mean of x bar is mu. The mean of p hat is p, which is what we had. And minimum variance, or the small standard error. And small error of estimation. The distance between the parameter and its point estimate is small. So what that means is, I want to focus on, if this is my unknown estimator mu, I want x bar, which is the point estimate for mu, to have a mean equal to mu, which is what we know we do in all cases. I want it to have small variance, which means I don't want the distribution of x bar to be like this. I want the distribution of x bar to be like this. That makes the variance smaller, or standard deviation smaller. And also I want the distance between mu and x bar. So x bar may be on this side, but I want the distance between them to be as small as possible. So these are good properties, and that's why we pick x bar and p hat to estimate mu and p, because these have good properties. Okay. Now, interval estimators. By contrast, you want to estimate the mean by a parameter. So instead of having just one point, I would say I want an interval to estimate my parameter. Okay, and so this hopefully around mu, but we don't know what mu is. That's the problem. So I'm estimating mu by an interval, and what properties this interval should have to be a good estimator. I want first, I want the probability that the estimator contains mu to be as high as possible, and I want the margin, the bound on the error estimation, to be as small as possible. So I want the probability that mu is here versus being there to be very high, and I want this interval also to be as small as possible, so mu would be captured in a small interval. And we call that 1 minus alpha is the probability of covering the mean. Alpha is the probability to make an error, that mu will be outside the interval. So these are the parameters we are interested in. If I have one population, it's mu. If I have two, if I have a binomial population, it's p. Sometimes I want to compare two quantitative populations. So comparing things means you look at the difference, mu1 minus mu2. If I want to compare two binomial populations, I would look at p1 minus p2. So we may or may not get to these in this course. So because I'm looking at all these properties together, I can summarize them. I can call any one of them theta. So this is called theta, and this is the way you write it, theta. Theta, theta is a Greek letter. So typically this is the process for any one of these parameters we go through. We collect data, and from the sample we keep track of the sample size, we keep track of the sample mean and the sample standard deviation, and then we want to pick the estimator for theta. I want to find out the estimator mean, so make sure it's unbiased. We want to calculate the standard error of x bar and make sure it's as small as possible. And for large samples, so assumption, we assume we have a large random sample plus others that we're going to specify in each case, certain assumptions that we need. Okay, so our interval estimators it's going to have, we have the point estimator plus or minus this quantity. We're going to talk about z alpha over 2. If you remember in the chapter on the normal distribution, when we talk about those critical values Z alpha. So we're going to talk about this a little bit, and that's the standard error of theta hat. So this is how we construct confidence intervals. It's the point estimate plus or minus the critical value times the standard error of the point estimator. If you remember this, it's going to always work for you. This will always be either a Z, as in this case, or a T. And so what is this? This is the value. Let me tell you what this one is here, and we clear this. So when we compute confidence intervals, we are going to need those values. Oops, this is my huge normal distribution. And I'm going to have, say, this point here, another point here, and another point there. So this would say, let's suppose this area is 0.10, this area is 0.05, and this area is 0.01. So what will be this? What will be the corresponding value here? And we know how to get this number as we go. This would be the 0, and if we look in the table, find this area 0.4 and go in the Z table and can read this number here to be 1.28, right? And for this being 0.4, this was the 1.645, where the area up here is 5%. This was the 1.33 or 0.326, where the area here is 0.01, and this area here 0.005, 0.5%, and this number here is 2.576. So we call this one Z 0.10. This number is Z 0.05, and this is Z 0.01, and this is Z 0.005. So these are the values, and we can have also the same values on this side, but with negative values by symmetry. So sometimes if I tell you Z alpha over 2, the question is what's alpha? So if alpha is 0.05, we didn't do the 1, or there's 1 here. See, there's 1 here also, where the area here is 0.025. If this area 1.025, this gives me a value here which is 1.96. Okay, so if alpha is 0.05, then this is going to be Z of 0.025, because that's half of it, alpha over 2, and that corresponds to the value 1.96 on here. So remember, it's not alpha, this is not, so this is the this is a subscript, tells me how much area I have in the upper tail. Okay, so I'm going to need those values, and a nice summary of these would be to write them this way, to get open another one. Do you want to open? Yes. See if I can. Oh no, that's not gonna work. So if to write this, Z 0.10 equal 1.28, Z of 0.05, and you may want to memorize these, or 1.645, or write them on a piece of paper so you can always use them. Z.025 is 1.96, Z of 0.01 1.326. Remember, some books use 1.33 or 1.32. Z.005 is 2.576. Again, some books use 5.8 or 5.7. So these are the values that we're going to use in this chapter and the next chapter. So now if we go back to this property here, remember those values. Now we deal with single quantitative population. The parameter of interest in this case is mu. So you collect data or sample data, we need n, x bar, and s, sample mean, sample standard deviation. We're going to specify alpha, and alpha is, talk about it in a little while, it's the probability to make an error. Its default value is 5%, as we saw in getting those z values, but it can be 10%, can go down to 1%. So the estimate for mu is x bar, its mean is mu, it's unbiased. It has sigma over square root of n as standard error, which means it has small variance. Good. So now the confidence interval for mu is going to be given by this formula, x bar plus or minus z alpha over 2. Now we know what that is. We call it the critical value, times the standard deviation over square root of n. And where 1 minus alpha is the probability that the interval estimator contains the parameter. The margin of error is just this part of it. This part of it, which is c alpha over 2 sigma over square root of n, and thus we call it the bound on the error of estimation, or the margin of error. Okay? So for these formulas to be valid, we need a large sample, and the sample also have to be random. So these are the two conditions: a random large sample. Random so that the sample represents the population, and large so that we can use the central limit theorem and just can use these z values. Okay, so let's go through an example to illustrate those ideas. We are interested in estimating the mean number of unoccupied seats per flight, which is mu, for a major airline. We don't know what it is, but we are able to collect a sample of 225 flights. We calculated the mean as 11.6, the sample mean, and the standard deviation as 4.1. So that's our data sample. This is x bar 11.6. So what's the point estimate of mu without the margin of error? That's just simply 11.6, the sample mean, x bar. So if I ask you a question, give me a bound on the error of estimation or the margin of error, but I want a 95% of a bound on the error of estimation. That means 1 minus alpha is 95%. That means alpha is 5%. And that would mean alpha over 2 is 0.025, and the corresponding z value would be 1.96. Okay, so 95% confidence means 5% alpha, alpha over 2.025, and the corresponding z is 1.96. So once you get that, the rest of it is going to be easy, because now we just give the formula E equals z alpha over 2 sigma over square root of n. We got this as 1.96, sigma 4.1, that's the square root of 0.225, and so our margin of error is about 0.54, about half a seat. So it's 11.6 plus or minus half a seat one way. So what if I ask you a question, give me the confidence in the 90% confidence interval. So again, that's the formula. Now 11.6 plus or minus, I want z alpha over 2. But now I want my confidence to be 90%. That means my alpha is going to be 10%. Okay, half of it is going to be 5%. So in this case, I need this value, 1.645. So I got the 1.645, 4.1, and square root of 2.25. And remember, so now my margin of the 90% margin of error is just this piece, which is 0.45, a little bit less than half a seat. So my confidence interval is 11.6 plus or minus the margin of error. I subtract, I get 11.15, I add, I get 12.05. So what does that interval mean? It means the interval contains mu with probability 0.9, or if I repeat it, sampling is used, 90% of the confidence interval I construct would contain mu. Okay. So if I show you the graph here, that means let me see, if I have a value here, I take my x bar here, I add my margin of error, subtract my margin of error, and I have a bell shape on that because of the central limit theorem. The area here is 0.9 and it's 0.05 here and 0.05 there in the upper tail, and mu is somewhere here, but mu will be here 90% of the time. Okay. So that's where mu, so I captured mu in that interval 90% of the time. Okay, so what's the width of the confidence interval? Oh, the width of the confidence interval. So if this is my confidence interval, that's my margin of error, the interval seems to be twice the width of the interval. So the width of the interval is twice the margin of error. That's a formula for it, and that's going to be 0.9. Has nothing to do with the 90%, it's just a coincidence here. If I increase my sample size, what happens to my confidence interval? Well, if n goes larger, the denominator gets larger, the whole thing will get smaller. So larger samples would give me a smaller confidence interval, which is better, and of course a smaller margin of error. Now if I tell you I want my margin of error not to exceed a certain value, can you tell me what sample size you need? And that's what I can use here. That's the formula, n approximately equals z alpha over 2 square sigma square over b square. So you tell me what margin of error you want, and I can tell you E or B. B for margin of error, same as E, and I can tell you what sample size you want. But to know sigma, you need to have some data, and sometimes you have it, sometimes you don't. But if you remember from chapter 2, sigma can be approximated by the range over 4. So suppose you want to construct a 99% confidence interval for mu, so that W is 0.06, which means basically the margin of error is 0.03. That's my margin of error, 0.03. So you're told that your data is going to range from 13.3 to 13.7. What sample size should you choose? So my alpha is 0.01, my range is 0.4, so my sigma, I can estimate sigma to be 0.1. My margin of error is the width of the interval over 2, and I use my formula. Oh, z alpha over 2, alpha is 0.01, I'm using alpha over 2, 0.005. The corresponding z value of this is 2.576, I want to square it. Sigma is 0.1, I want to square it. The margin of error is 0.03, I want to square it, and that gives me 73.7, so I round up to 74. Okay. Some exercises for you to do. If you double the sample size, what would happen? Sometimes you can be only interested in one side. If you look at this confidence interval here, I have a lower side and an upper side. But sometimes you may be only interested in one-sided confidence interval. You want to see whether your mu is below a certain level or above a certain level, but not in between two values. So in that case, that's your upper confidence interval, same as before, x bar plus, but you put all your area alpha, all your error in one tail instead of dividing it into two tails. So that would be x bar plus z alpha sigma over square root of n. If you want only the lower tail, it's going to be x bar minus z alpha sigma over square root of n. And note that we use z alpha, not alpha over 2 in this case. Okay. So next lecture we'll talk about small samples. where instead of using the Z distribution, we're going to use a more flat distribution called the T distribution. All right, take care.